So hello YouTube, welcome back to our radiation heat transfer learning journal. So it's just we have covered radiosity in the last video, and we found that this quantity is particularly useful for gray diffuse surface heat transfer. So radiosity is basically the combination of the amount of radiation coming from emissions, and you add that to the radiation coming off due to reflection. Okay, in this case diffuse reflection, so don't really have to worry that much. So the thing is, we have stopped there in the last video, and we have basically seen that Q net equals to the radiosity into the Q net dA1 equals the radiosity into dA1, which is whatever's coming off that surface, minus whatever's coming into that surface, which is HR. So what is HR for that gray surface? Then we have to take a look at the diagram to be very specific. Okay, know that for radiation heat transfer, always important to look at the diagram. So we're continuing this bit. Hopefully we can start solving problems by the end of this video. Maybe go through one example at most. Go through one example at most before we look into more complicated scenarios where maybe the medium in between is participating as well, so that we can sort of move into more complex scenarios that reflect real life heat transfer. So what is HR in this case? So HR, okay, very similar to the heat transfer. Okay, so it will be the component that comes from the outside, which is H0 R, okay, plus the component coming from whatever other surface there is. In this case, it is A2. So let's just put HR dA1. Okay, HR dA1, just to make it less confusing, so that you don't have to do mental division in your head to try and figure out, oh, is this per unit area or what? So I'm just going to put a no color highlight. Alright, so first thing first, we go into, that's the external component plus the sum of the internal components. So what is this? So we have what is the radiation coming from here to here? So remember, we need the view factor. Okay, so the view factor is just one part of it. Okay, the A2 to the A1. Alright, view factor is one part, and what is the total radiation coming off the A2? Now if the thing is gray, then we need to use the radiosity. So J. Okay, so I'll put J2 R and the A2. Right, so this is what we need to do, and then we'll need to add all of these components up across the whole area 2. So integrate over A2, this whole chunk here. Alright, so that's all we are doing. If we do again the same trick of dividing throughout and using the reciprocity rule, it means I'll divide throughout by A1 or dA1 in this case. Yep, and then we can use reciprocity rule to change this into the other view factor, which is dA1 to dA2. And this will become our expression for HR if we have the other side being a gray surface. So we can substitute that in here. And then we divide throughout by A1. or dA1 in this case, and we arrive at this expression here. Okay, so just to be sure, I'm going to put this as J1 because that's J from this side. Okay, and I think this R should be an R prime, right? This R should be an R prime because it denotes a different set of coordinates, because the first R is here, R prime will be here where A2 is. So I'll need to differentiate that. Okay, so that's all that it is doing. So if you were to do something like this, you bring the terms out, we will get an expression here. So I'm just going to highlight green because this is pretty important, what it looks like. For heat transfer, at least the heat coming off one surface into the other, at least from per unit area basis, from here to wherever else, radiating out. So that is equal to the radiosity, whatever is radiating out, minus whatever heat flux is getting from the outside, that's to say not from area 2, plus whatever contribution is coming from area 2 due to the radiosity. Of course, if this is a black surface, then we can use EBT to replace the radiosity if the other surface was black. But for now, we'll leave it as is. So now the thing is, it's kind of difficult. We have a bit of trouble still. We might know, let's say, no, EBT, right? That's well and good. And that will give us the intensity, right? But we don't know the radiosity necessarily. So the tricky part of solving the gray surface heat transfer is, of course, this radiosity problem, which we can start referring to the text to see how it's being treated. So what is being done in the text here? All right, since especially there's no participating media, whatever that is, yes, we can deal with it later. We find that it's usually best to eliminate radiosity. That means we just do a bunch of mathematical tricks to get radiosity out. So it says it's usually best to eliminate radiosity from equation 5.23. So what is 5.23? It is this equation, QR equals to epsilon r EBR into alpha r, which is the absorptivity, times h. So let's just write that down. Qnet QR equals to whatever this is, var epsilon. Okay, so why is there an r here? Well, that assumes that the emissivity kind of varies along this A1 here. In general, it might, but we can of course assume uniform emissivity throughout as well. That's another assumption we have to make if we want to simplify the calculations. But for now, I'm just going to leave it as such. EBR, because again, the black body emission might differ across the whole surface if the temperature has a profile. There's a temperature profile. Alpha R, and we'll need to substitute this whole expression for H here. So this is what is going on. Again, it's just restating the same equation in a different way, because previously we had the radiosity. Now we want to kind of get rid of it. So the other thing is to get rid of this radiosity as well. Okay. So the next thing is to express in terms of local temperature and heat flux, and eliminate the incoming irradiation H from equation 5.20. So what's equation 5.20? This is this here. Okay, this is the basic equation we kind of started with. Alright, so let's see if I've written this down already. I don't want to write it down again. Okay, here it is. Okay, I'm just going to restate it as alpha minus alpha HR, and that should be equal to, I'm gonna get rid of the dA ones as well, just divide throughout, because remember one minus rho is alpha in this case, so yeah, and that's equals to JR minus HR. Alright, so next thing we need to do, it's, what did they say? Expressing radiosity in terms of local temperature and heat flux, eliminating irradiation H. So it looks as if we are supposed to have two simultaneous equations and then just get rid of H. So how are we doing that? Okay, we'll have this equation one set, this one is the other one. Okay, so I'll just make H the subject, make HR the subject, and I'll get HR from this one over here. HR equals to JR minus QNet. Okay, then I'm going to substitute all that in here. Alright, then we'll have QNet 1 minus, okay, so let me bring that out first. Alpha QNet okay, 1 minus alpha. So what I'm doing is I'm just bringing this thing over, and then we get this expression here. And let's see where this train of thought is taking us. So we see that okay, Q minus alpha Q, which is what we have here on the left hand side, is equals to epsilon EB, yep, minus J, alpha J. So noting that alpha and epsilon is pretty much the same for our case, the next step is to make Q the subject. Then we have this very important equation here. So let's just do that. Okay, note alpha equals var epsilon, and what's the condition? Assumption of gray diffuse surface. Okay, then I'll just have var epsilon here. Okay, so we'll get QNet equals to var epsilon over 1 minus epsilon into EBT minus JR. Okay, this is an important equation to remember. You'll see why perhaps in the next few videos. Okay, so now that we have this, what are we supposed to do? Well, now that we have an expression for radiosity in terms of the heat flux, or the heat coming off that system, the prescribed heat flux coming off the system and the EB term here. Yeah. So we will then have an integral equation relating temperature T to heat flux Q. So what is that? Alright, so let's just do the substitution. Okay, where do we want to substitute? We want to substitute things in here. Alright, we want to eliminate JR from the following equation. The way to do that is, well, I need to rearrange some terms. So I'll need to get this out, definitely. So I'll just do like so. And I'll put this here. And I'll make JR the subject. Okay, I'll make JR the subject. Okay. Okay, let's see whether this lines up with what we have previously. I'm going to remove the highlights, if not it's too much highlight. Okay, so yeah, we have the same expression here, except it's arranged slightly different. So 1 over var epsilon minus minus 1, which is basically this second term. Epsilon divided by epsilon is just 1. Okay, so I'm just going to leave it like that. And the next step they want to do to eliminate this is to substitute everything back in here. Everything back into the first equation. So I'm gonna get this. Now we are ready to substitute. Okay. So we are specifically looking for the second surface. All right. Okay. So I'm just going to indicate all of this is with respect to the second surface, and this has to be, the coordinate systems also have to be with respect to the second surface. Okay. That's all I'm doing. I'm just saying, I'm denoting because it's r prime is the second surface. I put a subscript 2 because it's the second surface. And that's the same pattern I'm doing throughout. So I'm gonna take this and I'm gonna plug this in here. Alright, that's all I'm doing, nothing more. Yeah, so what is the next step? The next step is okay, so epsilon equals to alpha. So I'm going to divide everything throughout by that. So I'll just get rid of this, and I get rid of this. So that's part 1. Alright, so and then here we have two separate integrals, right? So let's simplify this. I'm gonna take the h not r out because that's kind of redundant. And now I want to separate out these two integrals. So, okay, so I just put the negative in front. Okay, just put the negative in front, and I'm going to copy and paste both of these over. So first thing first I want is this, the positive integral. Then I want the negative integral, which is the first term here. So I just copy and paste and get rid of this term. Okay, that's all I'm doing. And what is this then? How does this go over? It is just whatever is here, over here. Okay, so I'll just park this expression in, and we'll get something like this. We get something like this long integral here, and that is what we are left with. Okay, I mean it's expressed slightly different, sure. In the textbook we shift this term, oh no, sorry, we shift this term and the h term to the left side. So we'll just do that. Derivation is rather lengthy, and add h naught to both sides, and we are done. We have all the terms consisting of the heat flux on the left hand side, the external heat flux. All the terms with respect to radiation and temperature will be grouped to the right hand side. So that is our equation. Yep. Okay, I'm going to stop here for now. The next video I'm going to continue this discussion on gray diffuse surfaces. See you next time.